I'm going to talk about Kurzweil algorithm, which is an efficient algorithm for multiplication of large integers. Well, the naive algorithm multiplies each digit of the second number with all of the digits of the first number, or vice versa, then add them together to get the result. This takes a time complexity of n squared. Assume that we want to multiply 32 and 56. We can expand them like that. Now, if each digit was assigned to these characters, then by multiplying them, we get this. Now we can see that we have four main multiplications, ACAD, BC, and BD. Kurzweil aimed to minimize the number of multiplications. Expanding AD plus BC yields this equation. By storing the pre-calculated AC and BD values, they needn't be recomputed. Then, by performing one final multiplication of A plus B, all multiplied with C plus D, and subtracting the stored AC and BD values, Kurzweil made a solution in just 3 multiplications rather than 4. Now, let's dive into the algorithm design and strategy. The input will be 2 numbers, x and y. Each time, we will divide the 2 numbers into 4 sections A, B, C, and D. Before we calculate AC, we have to check if A or C has only one digit, therefore we will do the multiplication. Otherwise, we are going to divide AC into 4 sections again and repeat this step till reach A or C has only one digit, which is easy to be multiplied. Same thing is done with BD and AD plus BC. Finally, we are going to return this formula. Well, the strategy we are using is divide and conquer, since we are dividing each number into 2 sections and solve the small problems recursively and to get the bigger one. Here's the algorithm implementation. First, here's the base case. The base case checks whether or not x or y has only one digit. If so, therefore we are going to return the multiplication of them. Otherwise, we are going to divide the 2 numbers into 4 sections. A, B, C, and D, and then we are going to calculate AC, BD, AD plus BC. Let's take an example to make everything more clear. Now, if you take this example, this is a big problem, it cannot be solved. Therefore, it won't reach the base case, since the base case only needs one digit. So, we can divide this problem into sub-problems, then try to solve it again. So, we divided A, B, C, and D, and then call the function. Well, also this problem is big. It cannot be solved. Can we divide it into sub-problems? And then solve it again. Now, here we can reach the base case. We can calculate 5 times 3. So AC will be 15. Now we can call the function Kurzweil BD. So we can calculate BD, which is 3 and 4. BD is equal 12. Now, we can calculate finally AD plus BC. First, we are going to send them A plus B and C plus D. A plus B is 5 plus 3, and C plus D is 3 plus 4. Now, we can calculate 8 times 7, which is 56. But don't forget that we need to subtract AC and BD, which is 56. Subtracting AC and BD, therefore this is the answer. After that, we are going to return this formula. AC, BD, AD plus BC. Substitute in this formula. This will be the answer. Now we have solved these subproblems to get a solution to another bigger subproblem. Now, the same thing we are going to do with BD and AD plus BC. But for BD, this will be the formula, and for AD plus BC, now we can combine all these subproblems to solve the bigger problem, which is the answer. Now, if we substitute with AC, BD, and AD plus BC in the formula, this will give me the answer. Now, let's do the analysis. What is the basic operation? Basic operation is calling the functions, and since we are calling Kurzweil 3 times, therefore t of n will be equal to 3t. And since n is the number of digits for each number, and we are dividing each number into 2 sections, therefore the final analysis will be t of n will be equal to 3t n over 2. And for calculating the result of this expression, we can put positive 2 or positive 3 or even theta of n. It won't matter in the final analysis. T of n will be equal to 0 when n is more than 0 and less than or equal to 3. Otherwise, we will follow this equation. Substituting by t of n over 2, we will get this equation. Following these steps, we can detect a pattern and then generalize it. So we can see that n will be equal to 2 power k. Therefore, k will be equal log base 2 of n. So we can replace this pattern from this rule by this summation. After that, we can detect that t of 1 from the rule. We can see that t of 1 will be equal to 0. So 0 multiplied by 3 will be equal to 0. After that, we can see a rule that we can exchange the 3 with n. with n. Therefore, we can see that the final analysis will be equal to n log base 2 of 3.